Hi everyone, my name is Jacques Marquis and I'd like to talk to you today about a game called Snakes and Ladders. Now, this is a game I'm sure most of you, if not all of you, are already familiar with, but just as a refresher, I'll be going over the rules in a moment. Something that you may not be so familiar with is the history of the game. The game actually originated in India in the 2nd century BC, where the game sort of represented good and bad karma, with bad karma being the snakes that you'd slide down, and good karma being taking virtuous action in your life. The game today is a lot more light-hearted and usually considered luck-based, but there's a lot of maths that's hidden within it. Just as a quick overview of the rules, we always start on square 1 in the bottom left, and aim to finish on square 100 in the top left. You get to roll a 6-sided dice every turn. If you land at the bottom of the ladder, you immediately climb to the top of it, and if you land at the top of the snake, you'll immediately slide to the bottom of it. If you were, say, on square 97, to win, you would need to roll exactly a 3. If you rolled a 4, which would take you to square 101, then you've gone bust, and you have to wait till your next turn to go again, starting at square 97 again. So, using Python to model snakes and ladders, ironically, we're able to simulate the game pretty comfortably, and I simulated 100,000 games and kept track of the amount of turns each one took to win. That's plotted on the right-hand side. What's interesting about this is that even though the average, the sort of peak of that, seems to be somewhere around 40 turns or so, we've got what we call a positive skew. And you can see that because there are games which take over 300 turns to win, which really is quite unexpected, but is as a result of all those snakes which take you all the way back to the beginning. But this is an approximation, and we can do better, which is why we use the Markov model. I'm going to very briefly talk to you about this matrix here. This is called the transition matrix. And for those of you that don't know, a matrix is just a really big table of numbers. At least this one is. It's 100 by 100. And it's so big that instead of putting numbers, we just put colors. We're color coding it, and the darker it is, the bigger the number. So you can see some dark squares in the bottom right. And these numbers go between 0 and 1. What this table is actually telling us is it's a big map of all the possible probabilities to do with our board. So the probability that you get from one square to another move. And by multiplying this matrix to itself in various different ways, we can find out a bit more. We can find out the probability of moving from one square to another in 2 moves, 5 moves, 10 moves, so on. And this is what lets us plot this lovely black bold line over the top of our last graph. And this is the actual distribution of how long each of the moves will take. This has an average of around 55 moves, which, if you were to take 5 seconds to move, will take you 17.5 minutes to play a normal game of snakes and ladders. But what I wanted to talk about today was just how bad can a game of snakes and ladders get? So what I mean by this is, if we can put the snakes and ladders wherever we like on this board, how long can we expect the game to take? So some grounds of assumptions that we can make off the bat. If we want to make this game really hard, we should scrap the ladders. Ladders just help you, so let's make it snakes and snakes. And instead of having a snake lead you back to square 20 or square 10, let's have it take you all the way back to the beginning every time. So we've got snakes that lead back to square 1 and no ladders. But there's another thing that we need to differentiate between. And that is what we call infinite and finite boards. So the reason I've labeled the leftmost board infinite is because you can't win. No matter what you roll with your dice, you'll always hit a snake and you can never progress. However, on the right-hand side, if you were to roll a 4, you'll get to square 5. And if you were to roll a 4 again, you can win, you can reach the end. So some of you might say, well, the infinite one is harder, which, yeah, I guess so, but today we're only going to consider finite boards. So boards you can actually win. And we're going to see just how bad they can get. Now, just as a note on notation, to make this easier to read for bigger boards, I've taken away the tails of the snakes, and I've made the squares green instead. So each time you see a green square, it's a snake that leads back to square 1. Now, this is our first idea, and you can see this already looks pretty bad. We start on square 1, and we want to get to square 100, and the only way we can do that is if on every turn we roll a 6. And there's a lot of 6s that we need to roll. There's actually 17 of them here. And if you try to work this out on a computer to see how long this will take, this will be a really long time. It's a really sort of tough problem for it to manage. So I'm going to briefly mention that we try and simplify this using what I call the frog and the ladder problem. Now, very briefly, what this is we have a frog and a ladder, and the frog wants to jump up the rungs of the ladder, and it will do that with probability P. For us, that corresponds to rolling a 6 with your dice. So P is 1/6. If there's anything else, if you roll anything that's not a 6, then you'll fall all the way back to the start of the ladder, the same way you'd slide down a snake back to square 1. Now, doing this, we can find that the board I showed you a moment ago will take 17 perfect moves, and you'd expect, if you spend 1 second for each move, which is pretty generous, rolling a dice, moving your piece, realizing if you're on a snake or not, and going back, it would still take you 107,000 years to complete the game. 107,000 years ago, woolly mammoths roamed the earth, we were in the middle of an ice age, and if they'd started that game back then, they'd be finishing up any day now. We can do better than that. And this one's pretty good. The last one was a bit hit or miss, but this one's a pretty good guess. So the difference this time is that instead of having to roll a 6 every time, we now need to roll a 4 every time. The reason this is still good is because on any given roll, say I'm on square 33, the only way I can progress is by rolling a 4. There's no other options. So I have to make that 1 in 6 jump of rolling a 4 every time. And because we're making smaller jumps, I'm going to have to do more of them to get to square 100. Now, this means that we have to do 9 more perfect moves to get this one, which the number grows really quickly. This takes 6 trillion years to finish. Now, 6 trillion, that's a big number, and it's actually around about 1,000 times the lifespan of our sun. But this board isn't the best we could do. We can go one better. And it's this board. It doesn't look too nice. It looks a bit mismatched, asymmetrical. But there's something really important happening here. And it's that if we look at not the orange squares which are next to each other, but ones that are 1 apart, say 1 and 8, we've got one in between them, or 4 and 11, 8 and 15. They're a distance of 7 apart. And that's our sort of magic number. If they were any closer, if they were 6 apart, say this orange square on 8 was on square 7 instead, then when I start the game, I could roll a 6 and completely miss that square with 4 on it. That's going to make the game easier, not harder. You're just giving yourselves more ways to succeed. So this is the kind of rule we need to keep up throughout the whole board to make this as horrible as possible. And by doing this, by making these gaps precisely 7 apart on every other orange square, we can make it a bit harder, so that we need 3 more perfect moves. And this is the problem which grows exponentially. So 3 more perfect moves means we've gone from 6 trillion years to 1.4 quadrillion years. This is the last one. This is the best that we can do. if it's any closer together. We said we're making things easier. But what is 1.4 quadrillion years? Well, if we were to be flying on a rocket, and we were to start at the start of our game, and we were to play continuously while we were playing Snakes and Ladders, we're going to be flying continuously, then we'd actually have enough time to cross the observable universe 10 times over before you finish Snakes and Ladders. And I have a confession to make, that when I came up with the title of this talk, I called it a 1,000-year game, and my hope was to find a game which is so horrible that it could possibly take 1,000 years to complete it. I think we've done a bit better than that. I'd like to open up the floor to any questions.
Yeah, how did you figure out that 29 in fact was this optimal?
Well, so if you look at this kind of board here, if you had any of those squares close together, then you'd be able to sort of reduce the problem all the way back to our first guess, where the orange squares were 6 apart. And so we could do things in sort of less number of moves. So we've got 29 moves that we need to make here. If any of these squares were closer together, we could skip one of those moves. We could possibly do it in 27, 26, 25. Each one of those gives you the kind of scope to do things faster. So by spacing them just far apart enough, because it's only 100 squares, there's only so many you can fit. And this one, it seems to be 29.
All this theory that you developed here, is there anywhere else you can use it?
Yes, so Markov chains are an area of probability which don't just have uses for board games. Something like this with Markov chains which we used earlier on in our field to understand the board normally. This is the kind of theory which is used in your phones right now with autocorrect. You might look at, if you were to type a certain word, what's the most common word that we would type next? If you typed in your first name, your phone may look back through everything you've ever typed following your first name. And maybe it'll say, okay, well, he's probably going to type his surname next. So that may be your number one sort of recommendation from autocorrect. So there's uses outside of Snakes and Ladders, thankfully.
A historian and me think about this is that we have an awful lot of stakes and ladders type games going back quite a long way. And I'd be intrigued to know how long historic games would have taken to win. Because I suspect you could tell quite a lot about society by doing that. It's about how fatalistic people feel in that society, whether they expect to win, whether the life lesson children should be learning is patience, or whether the life lesson children should be learning is that things come good for you, and we're telling you quite a lot about wider society. Have you done any of that, of looking at older games and just seeing how long on average they would have taken to win? So it would be really interesting historically.
Right, so traditionally actually, these boards, whilst I haven't found the number of moves that take to win, it is a useful sort of thing which seems to appear in all of them, even in modern boards to this day, but especially the older ones, is that snakes are a lot longer than the ladders tend to be, and there's more of them. So because of that, falling on a snake seems to, on average, have a worse outcome than climbing up a ladder is. So you've got this kind of bias towards starting again. And the idea about it was that it was harder to live a virtuous life than it was to fall down the wrong path. It was to sort of demonstrate how easy it was to fall down the wrong path in your day-to-day life.
It's also human psychology. We're more sensitive to loss than we are to gain. That's really interesting. Any other questions? Jacques, many thanks.